Hi, I am Khushi Ladha, and today we will be talking about the Huffman coding algorithm. So, Huffman coding algorithm is basically a data compression algorithm, and it is used in file compressors, image processors, and image compressors, etc. It is a lossless data compression algorithm, meaning that compression happens such that no loss of information occurs. And it uses prefix codes. So prefix codes are basically variable length codes that are assigned to the input characters, and they are decided on the frequency of the occurrence of input characters. These prefix codes have the prefix properties, meaning that there is no whole code word in the system that is a prefix of any code. So for example, if we have two input characters A and B, and if we assign the code of A to be 11, then for B the code value cannot be 110 because the 11 part is common to both A and B. So if this prefix property is satisfied, that would mean that each character would have a unique code value. The goal of this algorithm is to reduce the total number of bits without losing any information. So let's see an example. So assume that we had a sentence and we extracted all the letters that were present in the sentence, and we uh, wrote the frequency of all the characters. Uh, so after the letters and their frequency has been written, codes were assigned to the characters, and all these codes are three length codes, meaning that they are of fixed length. And after the codes have been assigned, the total bits are calculated. So for example, for the letter E, the occurrence of the frequency is 15, and the code value is 000. So the code length is 3. So the total number of bits for E letter would be 45. Similarly, the total bits are calculated for all the other characters or all the other letters, and they are summed up, and in this example the value turns out to be 156. So the Huffman coding tree of like the tree for this particular example would look something like this, with all the letters present at the leaf nodes of the tree. The left traversal would mean a value 0, and the right traversal of this tree would give us the value 1. So if I were to find the value of the character n, I would start from the root node, and then from root node I would go to this node. So we would get the value 0, and after going to this node we would go to this, and then finally this. So the value would be 0, 0 and 1. Similarly, values for all other characters can be obtained. So if you apply the Huffman coding algorithm, our table would change to something like this. So for applying the algorithm, what would we basically do is that sort the frequency of occurrence of all the letters, and for the values that have higher frequencies, the code that is assigned to it must have the least length values. So for example, over here E had the frequency of 15, so its code's length value is 2. N had the code length 2, and N had the frequency 10, so its code length is 2 and its code value is 0, 1. For V, the frequency was comparatively much less, so the code length is relatively larger. Now, why does this work? Is because that uh, when we are calculating the bits, so the bits would be the product of the occurrence of the frequency, like the frequency value, and the length of the code, that is 2 over here. So in this example, the total bit count would be 30. If the character with the highest frequency is assigned the code which is having the least value, then naturally this bit size would reduce, or we can say that the bit value would reduce. So if you calculate the bits for all the characters and sum it up, in this case it would turn out to be 132, and it is relatively lesser as compared to 156 when the codes were of fixed length. So yeah, taking up variable codes of variable length does reduce the bit count. We can see in this example, and also this algorithm is lossless because if we see over here, initially we had got information about the letters and their occurrences, and this information is still retained. So this is the Huffman tree of that previous table. Let's see how it was made. So here is the pseudo code for the Huffman algorithm. So initially the characters and their frequency values have been input over here in this C set, and then they are stored in this queue. So the queue would have the values, the frequency values as 10, 12, 2, 4, 4, 5 initially. Okay, and then there are like 7 characters in our examples. So the value of n would be 7, and there are a total of n minus 1, that is 6 internal nodes present. So we would be applying a for loop to go from I equal to 1 to n minus 1 to basically fill the internal nodes of the tree. So like for the first example, to allocate when we are making this tree from the scratch, we would first allocate a new node z, and then the children of the new node would be those two values, those two characters which had the least frequency. So we would use the extract min operation from the queue to obtain these two values. One of them would become the left child and the next one would become the right child. And the parent would have its value to be the sum of the frequencies of these two, that is 2 plus 4, that would be 6. And then this node would be stored into the queue again. So in one for loop, we would be applying 2 extract minimum operations and 1 insertion operations. So the net would be 1 element is always removed from the queue. This loop is again repeated. So after the first operation, this 2 and 4 would be removed from the queue and 6 would be added. So our queue would be having the elements 10, 12, 2, 2 is removed, 10, 12, 4, 5 and 6. Now again a new node would be allocated in the next loop. So the new node would be this one. The value won't be present over here right now. After that, the extract minimum operation in the queue would be performed again, and then the value would be turned out to be 4. Again, once again it is applied, and the value would be turned out to be 5, and then they would be assigned as the children of this new node, and the value of the parent node would be the sum of the frequencies of these two nodes, so it would be 9. Since like the new internal node that was formed in the first loop had value 6, which was higher than uh, the frequency value of the two characters 4 and 5, so we had to make a separate subtree for these two nodes. If this value was, say for example, 3, and these two values were 4 and 5, then we would be taking up 4 and 3. So when we are moving to the next loop, again this process would be repeated. Uh, 2, 4, 4 and 5 would have, and 6 would, 2, 4, 4 and 5 would have been removed from the queue, and after that 6 and 9 would be the next two smallest elements, so they would be picked up from the queue, and they would be made the children of this new node, and then after making them the children, they would be removed from the queue and 15 would be added to the queue. Again this process would be repeated, and 15, this e character would be added along with this 15, and then we would be having this node. So this process keeps repeating till we get this final tree, like it would be repeated 3 more times after we left. So after n minus 1 executions, we would basically be left with this part, and our for loop would be completed. and the last element that would be left in the queue would be the root node. So we would get it as the last element that we can see in this code, that the ninth line tells return the last element and it would be the root of the tree. Yeah, so after this, yeah, so Weissman once said that an algorithm must be implemented to be believed. So let's just, so there is this image file which is in PMP format, and let's just run this code once. So the images, they have the pixel values, and for these pixel values codes have been generated, and you can see them over here, and the average number of bits is nearly like 7.6. Now coming to the time complexity, we had n number of characters, and extract minimum is called 2 into n number of times, and each operation of extract minimum takes O log n because it calls CP5. So the overall complexity would become O n into log n. So yeah, thank you so much for your attention and for your time. The GitHub link of the Huffman code is present in the description, so you can check it out once and implement it on your own machine.